See, that has nothing to do with my hearing. It has to do with something else. Okay. So if you're going to sleep, you need to leave, and I'm not directing that to anybody in particular, but I think we all kind of, it's fairly obvious. Yeah. Or if you have something you need to talk to somebody, ongoing conversation. So we're going to continue on talking about thermodynamics, and an important principle in being able to count on keeping track of energy is the conservation of energy. There's a lot of conservations in physical science. There's a lot of conservations in this universe. My hearing. So conservation of energy. That's assuming, I guess, conservation of energy. Did you need that back again? Okay. That's assuming that there is no sort of nuclear reaction that is converting, that's creating energy out of matter. Okay, so we're not doing that sort of this. Okay. So I'm going to draw a little picture when I think of these terms, and they're very applicable when you start to do thermodynamic problems. Okay, we'll be talking about what we call a system of interest, and I am famous for my beakers, as you know by now. Okay, so the system would be possibly the contents of a beaker. Okay, so that would be the system of interest. And of course, in this case, you can clearly see the boundaries of the glass, right? Actually, we have a couple interfaces. We have the glass interface, and then if it's water or liquid or something, you have a liquid and air interface. So that would be the boundary. And then the way this works is anything outside the system of interest is the surroundings. Okay, so those are kind of a visual sort of thing. So we'll go back to the beaker. Okay, if our system is isolated, which actually we're going to make that assumption, but you know what they say about assumptions. So you break it down, it makes an ass out of you and me. Assumption, yeah, assume, makes an ass out of you and me. But if we assume that it's isolated, actually it could be one of two things. We could say it's isolated with regard to matter. That means matter's not going to enter our system from the surroundings, nor is matter going to go from our system to the surroundings. Or energy. Energy's not going to go across that barrier. What's in the system stays in the system. Okay. Similar to energy momentum. So sometimes, though, and we're just going to kind of talk about an isolated system in terms of nothing crosses the boundary. Isolated that in terms of matter and energy. Isolated. But in some cases, there's a distinction between closed and isolated. And closed is reserved for mass cannot cross the boundary. And isolated is for energy not crossing the boundary. So here is our first, we're going to work this problem. And I thought about passing the iPad around. I'm still not done with that idea. Okay, but I think when I looked at what would need to be calculated, it just doesn't lend itself. So when we read this problem, be thinking of the system. And I think I'm going to sit down to draw this. When I work these problems, I have to read those words several times. And I basically, like you've seen me do, lift those words out and put them on a diagram. So the thing here is we have two objects, aluminum, and this will hopefully become apparent as we work these. We have aluminum and we have water. Those are our two objects. And they are the two objects that are going to occupy the same system. So if you read it a few times, what you will see is, and I usually draw my metal out to the side here. Here's my aluminum. Okay. And then if you read it a few times, you can see that they do this a lot. They being people who make thermodynamic problems. We're going to take that piece of aluminum and we are going to douse it into my beaker of water. So it'll eventually look like this, okay? Does that make sense? And this is water. I'll just put water up here. Okay. Now, I guess an important thing to review, this is Wednesday. On Monday, we came up with the fact that either object, either the aluminum or the water, we can talk about its change in thermal energy. And you guys did homework problems, 7, 1, and 2. we can talk about the change in thermal energy was related to the mass of those objects times the specific heat of those objects times the change in temperature that those objects experience. So there at the top says Q is equal to MC sub P delta T. I need to finish this thought. Let's diagram this. So it says my aluminum, it says of unknown mass. So actually, and you're going to see me use little subscripts. I'm going to put M sub AL, that's the mass of the aluminum, is equal to question mark. You know, and sometimes I'll diagram them different orders, okay? But then I'm going to take that next number, C sub P, and that is the specific heat of aluminum. I'm going to put that over there. It's kind of like a tally card. And I'm going to make sure that I give it a C sub P sub aluminum. And I'm going to go ahead and unpack those units. Remember, I hate that J/G/degree Celsius. I don't know who came up with that. But it's 0.902 joules per 1 gram per also degree Celsius. That's specific heat aluminum. Then notice it gives me some more information about the aluminum. Part of your job is to kind of make sure you get the right information with the right thing. So my aluminum is heated to 98.7. Now, can you see, and I'll put under here, I'll expand on what we talked about on Monday, that delta T, we said change in temperature is always going to be what? Final minus initial, right? So the aluminum's going to undergo a temperature change and the water's going to undergo a temperature change. So can you see as I'm reading kind of that first sentence, it gives me aluminum, blah, 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 specific heat, blah, 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 is heated to 98.7 degrees Celsius. If you read this a few times, that's the initial temperature before I douse it. I like the word douse. So actually, when all's said and done, the initial temperature of your aluminum is that 98.7 degrees Celsius. Okay. Where are we? Now a cup of coffee. Then it gives me some information about the water, right? It gives me the mass of the water, which is cool. So over here under the water side, I'm going to say M sub water, M sub H2O, is equal to 50 grams, 3 sig figs, 50.0 grams. And then it gives me some more blada blada. The initial temperature of the water was, so I'm going to put T sub I water, 22.2 degrees Celsius. See how it just, Ti sub H2O. Things just kind of start falling into place. All right. Now, that last sentence before the question says, when thermal equilibrium was reached. Okay, so here's where we kind of have some action going on. We take the hot aluminum, we add it to the beaker of water, which happens to be a mass of 50.0 grams. The water is what going to heat up, okay, and the aluminum is going to cool down. It's important in this sort of problem that when they talk about an equilibrium temperature, that is the final temperature of both the aluminum and the water. So actually, I'm going to put that 33.3 under T sub F of aluminum and T sub F of H2O. Since I'm over here first, T sub F H2O, 33.3. And the cool thing, no pun intended, and that's also the temperature of the aluminum. What was I going to say? Oh, it should make sense to you. I mean, you know, you can all picture taking a hot piece of metal that's almost 100 degrees Celsius and putting it in water that's 22.2 degrees Celsius, and the water's going to heat up and the aluminum's going to cool down. All right. So I'm going to show you something, and then my next few slides kind of explain why this is the case. So we have two objects here, but the two objects occupy the same system. And then what is it? Oh, I know. I was listening to a sermon one time recently, and the guy said, yes, you agree? So let me show you what I mean. Our system is the beaker, and so this is the beaker. And so actually, I'm going to say that the change in thermal energy of the system, okay, is equal to those two objects, the water and the aluminum. And again, I'm going to kind of belabor this in a few slides coming up, but it should go fast now. I'll explain it. Our system. And what did I say a minute ago? We're saying this, if they say the system is isolated, is there any energy leaving the beaker and coming into the beaker? No. So Q is change in thermal energy. So if it's isolated, the change in thermal energy of the system is equal to 0 if it's isolated. So what the heck? I'm going to go ahead and make I don't like doing this. I'm going to go ahead and make kind of an equality triad here. Q the system is equal to the two things we're talking about, the water and the change in thermal energy of the water, change in thermal energy of the aluminum. And that's equal to 0 if it's isolated. The beauty of this is, can you see where we can now say, you can, however you want to say it, say like subtract Q of aluminum from both sides. Okay, and you get Q of water is equal to negative Q of aluminum. It's like a math thing. Okay, conservation of energy. So bottom line, and this kind of reminds me of stoichiometric calculations. Do you see where we have enough over here? I know it's kind of scribbled. But do you see where we have enough on the water side to come up with the Q of water? Q is equal to mc sub p delta T. Do you know the mass of the water? Do you know the specific heat of water? Mm-hmm. You know the delta T water? Yeah. So basically, we can come up with the Q of the water, and that's, by golly, equal to negative Q of the aluminum. And then, if it was you, might as well. Thank you. And so once we have the Q of the aluminum, we can use Q is equal to mc sub b delta T for aluminum, rearrange it, and solve for M. I don't know if that makes sense, but that's what we're going to do. All right. Okay, so I kind of got ahead of the gun, but in order to work this problem, I kind of told you that we're going to have to assume that there's no energy crossing the boundary. It's isolated. That aluminum and water can swap energy all day, but they can't take anything from the surroundings, nor will they give anything to the surroundings. So there is a type of problem, and I'll have to try to catch up when we get to the sort of homework problems, but there is a type of problem where you introduce something of the Q of the bomb, the Q of the, sometimes it's called Q of the calorimeter. That's the beaker that's holding the thing. You have to introduce a term. But we're assuming that that glass beaker doesn't interact at all. Okay. So in this particular case, and this is classic in your homework that's going to be due on Friday, and classic in this sort of problem, you basically got two objects that are swapping thermal energy. Kind of gross if you think about it. The hot thing is giving up its thermal energy, and the cooler thing's taking in its thermal energy. And don't forget the important aspect of they both come to the same equilibrium temperature. So specific to this problem, as the aluminum cools down, it gives its energy to the water, and as the water heats up, it got its energy from the aluminum. All right. So by definition, an isolated system, the change in thermal energy of the system, the change in thermal energy of this contents of that beaker is 0. It's a wash. But that's not to say there's nothing going on in the beaker, because like we said, the aluminum is cooling down. It's got a change in thermal energy. It's cooling down, and the water's heating up. Okay, but they have to add up to be equal to 0. So that's why kind of a quick rearrangement on the next slide, and you have that in this case, they are what? Equal in magnitude but opposite in sign. Okay, and sometimes there will be a third or a fourth term, basically telling you something is going on in your system. Okay, you have to account for all terms. Sometimes there's multiple terms. Okay. So when you're working problems, there are definitely times when you're going to get to this relationship. You know, you have an object giving up thermal energy and an object taking in thermal energy. There's only two things going on there. So like I said, they are equal in magnitude but opposite in sign. But you have to state this. Keep track of your beans. So I already kind of told you that if you look at the two things, the aluminum and the water, and it's kind of like working titration problems. We know a lot. We know everything about the water to get Q, but what we need to get is the mass of the aluminum. And we can go through it this way. Oops. So I diagrammed the information, and actually, so this is stuff what was on the right? This is all stuff about the water. Q of the water, the mass was given. Specific heat of water will not be given on your Unit 3 exam, okay, but you'll need to know the specific heat of water. I would stick with joules. The initial and the final temperature were given of the water. But make sure you have to show all work, blah, blah, blah. You have to show this subtraction. And actually, it's in your best interest. You can cover your butt if you made an oops, at least I can see where that came from. That's our delta T term. So the next thing you're going to see basically is plug these three values into that equation, you know. And when you do so, just kind of like you did for your homework, the homework that you handed in today, when you do so, you need to make sure that you have the units of mass or grams, the units of heat units of specific heat are joules per gram degree Celsius. The units of delta T are degrees Celsius. With that said, remember that temperature scales are kind of a good relationship between Kelvin and Celsius. That honestly, you can use a specific heat that is in Kelvin and have the temperature change in Kelvin, and it should be the same in Celsius. So when you knock this into your calculator, remember you're going to have to give it three significant figures. So you get the Q of the water is 2.32 times 10 to the third joules. So now one of the things, working this sort of problem, I think I mentioned it before, is just make sure that you use little subscripts. Because you have two Qs, you have two Ms, you have two Tis, okay? Two delta Ts. Say what it is you're talking about. So this is the Q of the water. Now we're ready to go for the Q of the aluminum. And you need to show this step. Oh, it sounds silly. But simply, if the change in thermal energy of the aluminum is negative change in thermal energy of the water, we got that too. So the change in thermal energy of the aluminum is negative 2.32 times 10 to the third joules. In my, there's going to be 4 problems that are due on Friday, and in my answer keys, Monday, oh, thank you, Monday. We don't have class on Friday. In my answer keys, I use the word rearrange, because honestly, I would probably go ahead and rearrange Q is equal to M C sub P delta T to solve for what it is you want to get out of this. So if you look back in your notes, you can see that we are after the mass of the aluminum. Okay, so rearranging Q is equal to M C sub P delta T. M is equal to Q divided by C sub P delta T. And back in your notes now, you know that we just found Q of the aluminum. The specific heat of aluminum was given, and of course we have the initial and the final temperatures, so we can knock out delta T. But don't forget to knock out delta T's, show your work. So this is all the stuff about the aluminum. So the equilibrium temperature, the common temperature of the aluminum water was at 33.3. Remember, it was heated up to 98.7. And this is what we talked about before, too. If something cools down, like this, the final temperature is less than initial temperature, it ends up with a negative delta T, which ends up with a negative Q, right? So that's all good. So keep your signs. So plugging in the Q that we found from the Q of the water, and the specific heat of aluminum, which was given, and the delta T of aluminum, which we just calculated by subtraction, this is what we end up with. So I'm going to show you how units cancel. Let's see. Units of joules up here. Oops, that's nice and deep. Units of joules right there. Okay. Do you see where I call this the joules is in the numerator of the numerator, and here joules is in the numerator of the denominator. Okay. Bottom line, they cancel out. The units of degrees Celsius in the denominator cancel out. This happens a lot in physical science when you are using unit analysis or dimensional analysis to see if you got the right answer. Unit-wise, we end up with basically that. 1 over grams. And we can resolve this situation by taking that ratio from the denominator, if we want to pull it up and put it into the numerator. Basically, that's equal to 1 over 1 times grams over 1. I don't know how to explain that. I'm not a math teacher. But something in the inverse of something in the denominator of the denominator can be brought up into the numerator. All right. So round of 3 sig figs. The other thing is, notice that if you have two negatives like this, we have a negative for our Q and we have a negative for our delta T. That's cool, because two negatives are positive. And by golly, if your mass is negative, you're in the wrong universe. Okay, so 3 sig figs, you should get 39.4 grams. So I just think this is exciting, where you can see the influence of the metal on the water changing its temperature and come up with an answer of the mass of the aluminum. Okay, so you did 71 and 72, which I like doing it breaking it up that way, because those were just isolated, no pun intended. Those didn't have kind of two things swapping energy. So let's take a look at these 4 right quick, and I think that they're already posted to the Twitter feed. I think I did that. But let me know if I didn't, because I've thought that before. Okay. So they should look kind of like this. And these look really busy, but let's kind of break it down. When you go to do it, you're going to have to read them a few times. I know I did. You know, don't be like, oh, I can't do it because I have to read it many times. No, you do have to read it many times. I do. And I don't know if you'll catch it, but I go back and forth. So reading it, you'll see that basically we're going to douse aluminum, kind of like we did this is silver. This is silver, and I changed this L to a G later. And we're going to put it into water. We're given the mass of the silver and the initial temperature of the silver. Okay. We're also given the mass of the water and the initial temperature of the water and the final temperature of the water. Notice that's also the final temperature of the silver. Okay? And I go back and change those L's to G's here in a minute. And notice, in this case, we're after the specific heat of the aluminum, the copper. You know what I mean. Ag, silver. Okay. So it does kind of remind me of working titration problems and seeing you know a lot about this, but not about that. So basically, it's water, so you're going to know the specific heat already. So we can use Q is equal to mc sub p to get Q of the water. Okay. And we have isolated system. So it looks like our hot metal is going to actually, again, give off thermal energy to our water. But that actually, if it's isolated, the change in thermal energy of the system is equal to 0. So then that means we have, again, this relationship between the metal and the water, the change in thermal energy of the silver is equal to negative change in thermal energy of the water. So kind of in 3 steps, I would calculate the Q of the water, and then set the Q of the silver equal to negative Q of water. And again, I like to rearrange and then plug in. I rearrange the Q is equal to mc sub p delta T, solving for C sub p this time. that's your hint for that one. The next one, that's my oven. Okay, so we have metal that we have heated up. Okay, and the mass of the metal is given. It's very similar kind of relationship, or dousing it in water. The mass of the water is given, the initial and the final temperature of the water is given, and looks like the specific heat of the iron is also given. Okay, in this case, we're supposed to find the initial temperature of the iron. So here's my oven. I could have put question mark temperature. Wouldn't that be cute? Okay, so here's my iron, or my oven. So we have hot iron that comes to an equilibrium temperature of 87, yeah, with no decimal, 87 degrees Celsius. Okay. So it's important that you keep in mind that when they talk about equilibrium, everything comes to that same common temperature. They have different delta T's because they had different starting places. Okay, so again, if we have a closed system, we only have two things that are swapping thermal energy. The energy given up by the iron is equal to the energy accepted by the water. So you have enough over here to knock out Q is equal to MC sub P delta T, the Q of the water. I would do that. I would recognize that, that they are equal in magnitude but opposite in sign, the iron and the water. Just keep in mind that sometimes you'll have a third or fourth term also in your system, okay, going on in your system, even though the change in thermal energy of the system is 0. You have a couple more things going on. So in this case, I would rearrange Q is equal to MC sub P delta T to solve for delta T. So you're going to get delta T this time, and you're not done. You need to remember, and I was talking to somebody at my office today, you think you're almost done. I got delta T, what's T sub I? Well, think about it. Okay, delta T, deltas are always final minus initial. So I would even write it down. Delta T is equal to T sub F minus T sub I. I'm after T sub I, so if I, well, I have to rearrange things. The reason I'm drawing a blank is because yeah, you just add it to both sides. Thanks. Yeah. I would have to write it out. So is this what you're saying? Delta T is T sub F minus T sub I. See, if I add T sub F over there, then I have a negative T sub I. See what I'm saying? So if you're after T sub I might multiply through by a -1. I don't know. -1, negative, plus, and then I would solve for T sub I is equal to T sub F minus delta T. Okay. However you do it, be careful. This is correct. Okay. It looks easy, but all right. Concentrate. Okay. 2 more problems. Again, they kind of have a similar thing going on. This one has stainless steel adding it to water. The stainless steel is heated up to 183 degrees Celsius. Okay, notice that we aren't given the mass of the water, but we're given volume. We can use density to get to mass. Okay, and we're after the mass. Here, you can set it up how you want to. SS means stainless steel for me. Okay, so we're after the mass of the stainless steel. Notice the specific heat of stainless steel is given. I think I forgot to put that in here. Okay, I was in a hurry. So again, you know enough with regard to, you can do volume to get to mass of water. You know the specific heat of water. You got the delta T over there. You can knock out Q of water. And it has this relationship with the Q, change in thermal energy of the stainless steel, of being equal in magnitude, opposite in sign. So once you have the Q of the stainless steel, then you can rearrange Q is equal to MC sub P delta T, solving for the mass. Okay, and then plug in the Q that you just got, the specific heat for stainless steel, and the delta T for the stainless steel. Again, be careful. Make sure these delta T's, you show that work. I hate taking off a point because you show the initial, you show the final, but you don't show the subtraction to get the delta T. But I'll do it. Okay? I know they have kind of a follow-up question. Feel free to answer these or not. One of the things about doing problems especially problems that you might potentially find challenging, is if you come up against something you're like, I don't know how to say how precise this method would be to determine mass, well, don't worry about that part. To me, the crux of the problem is, what is the mass? All right, last but not least, those are my little dots of copper. This time we're going to add copper not to water, but glycerol. The volume of the glycerol is given in the density of the glycerol, so we can get to mass of the glycerol. The initial temperatures of the shot and the glycerol are given. Notice that, I'll tell on myself, originally I didn't put these I didn't identify, this was for the initial and the final temperature of the glycerol, so I went back and added it, little subscripts. So when the dust finally settles, it's just a matter of what don't you know. So in this case, can you see where basically this side is filled out with regard to the metal? We have the mass of the metal, we can get the delta T of the metal, we have the specific heat of the metal, so we can knock out Q of the metal. And since it's a closed system, they have, I missed a negative sign tonight. They have this relationship, Q of the copper is equal to negative Q of the glycerin. So you calculate the Q of the copper, and then you set that, then you can find the Q of the glycerin just simply by multiplying it by -1. You rearrange Q is equal to MC sub P delta T, solving for the specific heat of the glycerin, and you plug in the Q that you just got, the mass which was given, you got from volume and density, and the delta T that you can get. So they're like little stories. Any questions? Cool. Well, I know I said we'd go on to the next part, but this will be a good, as long as you promise to not go brain dead over the weekend, we'll pick up with the next part on Monday. So these will be due Monday also. And remember, I do check my email between concerts.